Hey everybody. All right, so this is the last lab. This lab is a little PDF that you can find in Canvas under the last module where you'll probably find this video. So if you found the video, you probably have found the document, but the short little 4-page PDF. This title is Rotational Dynamics. Starts from the idea that translational kinetic energy, which you talked about, 1/2 mv squared. So a block going down a ramp has kinetic energy of 1/2 mv squared. And now we're also looking at rotational kinetic energy. So if we had a ball or a disc or a ring rolling down, it is rotating, and so that gives it rotational kinetic energy. So the total kinetic energy would be the sum of the translational kinetic energy, 1/2 mv squared, and the rotational kinetic energy, 1/2 I omega squared. I is the moment of inertia, omega is the angular speed. And then from, I'm not sure what chapter in your textbook, but we all looked at the work energy theorem. For a conservative system, when no external forces are acting, the kinetic energy equals the potential energy. So for this lab, we'll calculate an experimental velocity, or a theoretical velocity, and then we'll roll down some objects down the ramp and measure the velocity, and then compare the measured velocity to the theoretical velocity for a disk and a ring. So page 1 just shows you the formulas. And then after you use the work energy theorem, you'll have 1/2 mv squared plus 1/2 I omega squared equals potential energy, which is just mgh. And then you can plug in what omega is, which is use V equals R omega to get the translational velocity. And then you can solve that for V, which the manual does on page 1, and you get that equation, which will be the theoretical velocity. So with that theoretical equation, we just need to figure out what I is, the theoretical moment of inertia for the ring and the disk, and then we can have our theoretical velocity. So to set this experiment up, let me switch my camera. I got my little wood block set on the table. You're going to put it on an incline. So I recommend a very small incline. So I got 2 little old batteries that I'm going to use, but stick it under one end. Now you'll use your protractor to get the angle of your ramp. So if you still got the string tied to it with the weight, you can line the line up with the ramp angle, and then the string and the weight will tell you what the angle is. Or if you put it on the edge of the table and don't have the string tied to it, you can just put the protractor on the corner and then use the line from the ramp to actually see which degree that ramp intersects, and you get the angle that way. So wherever you do it, get your angle. Then you'll also get the length that the object's going to roll down the ramp. So we're going to start the object at the very tip of the ramp as close as we can. So mine's about 35.6 centimeters. And then once we know the angle of the ramp and the length of the ramp, you can use trig to get the little height of the ramp. So sine theta equals the height divided by the distance that we just measured, which is the hypotenuse. And then you can solve for h. So h equals d sine theta. So in that little first part of the lab manual, they asked for you to solve for h using a simple triangle. So tell you to do that. Then once we got the ramp set up, we'll need to get the dimensions of the ring and the disc. So the little scale they give you probably doesn't make the measurement. Mine only goes up to 100 grams. So I had to get another scale. So if that's the case for you, which you probably also have about 100 gram max range, I wrote the masses of these, which, we're assuming everybody gets the same one, which obviously probably won't be the case. But you can use those masses that are written down in the lab manual if you don't have the scale that can do it, or you can find a way to actually get these measurements with a better scale. But don't go out and buy anything, please. So this is all you got, just use the numbers I gave you in the manual. And then we're going to use these calipers to measure the radius. So you'll measure the radius of the disc, use the calipers, close it in, and then make that a reading. Probably can't see my scale, but I'm at like 114 point, wherever they overlap, 114.1 millimeters. That'll be MR, sorry, R. And they did the ring first, so of course. So yeah, they did the ring first. So weigh them both, then outer radius you can measure with these jaws. So outer radius will get measured with that. And then for the inner radius, use the little ones on top to go out and make that measurement. So inner radius, outer radius. So first part is for the ring. So we've got the mass of both. We got the inner and the outer radius of this. So that's the diameter. Sorry, this will give you the inner and outer diameter. That'll be DI for inner, DO for outer. And then once you've got the diameter, you can calculate the radius just by dividing by diameter by 2. So you'll get the radius, and then you'll need to calculate the theoretical moment of inertia. So on page 1, actually it's on page 2. So number 3, I sub r is 1/2 m times the square of the radiuses added together. So 1/2 m times I squared plus RO squared. So we know m, 131.7 grams if you use the number I gave you. RI and RO, we calculate. Mine came up to be roughly 56.75 and 53.9 millimeters. So you can plug all that in there and get the moment of inertia for our little ring. Once you got that, you can plug in that I into the very first equation we looked at, and get the theoretical velocity. So G, gravity, H, you just got the height of the ramp. 1 plus I, that's the number we just got, over mr squared. So you know M and you know R. So for this one, use the outer radius as the R in that equation. So that is one slightly confusing. So that'll then give you a theoretical velocity. Mine came out to be about 0.25 meters per second. So after that, you'll then actually do the experiment. So place it up at the very top, get your stopwatch timer out, and once you release, you start it. So I would start from rest and then release and start. And so I'm going, yeah, move it over, move to left or right as I move, because you could have a slightly flat spot on the ramp. So there we go. I'm a little higher on the ramp or closer to the camera. So now release, start, and stop. So time it from top to bottom, and then you can do, I think it says do 5 trials. So do 5 trials, and every time on a little piece of scratch paper, write down the number. And then once you get through the 5 trials, take the average of it. So my average, like 3.5-ish seconds or so. Once you got the velocity, I mean the time, you already know how far it went. So then you can use the equation from page 1, which is 2 times the distance divided by the time it took to go down, which is an equation y'all have used in some of these other labs to calculate the experimental velocity at the bottom of the ramp. So that's part 1. And then part 2, you do the exact same thing with the disc. So you already got the mass of the disc. We already kind of accidentally measured that diameter. So there's the diameter. Divide that by 2 to get the radius. Once you got the radius, you can calculate the theoretical moment of inertia. You know the mass and radius. And then you can plug that into the theoretical velocity equation. Get your theoretical velocity. Mine came out to about 0.285, so slightly larger than it was for the ring. And then same thing, just start at the top, make sure you're down in a little flat spot I just found, and start. Oh, still there. So you'll start, stop, time 5 trials, get the average, and then you can calculate the experimental velocity. So once you got that, you'll calculate the percent difference between the theoretical and the experimental because they're both different measurements. That's why we're doing percent difference. So percent difference is just percent difference is just the difference over the average. So that should be a pretty quick calculation. And then that's it. There's just the two parts. So you'll get the theoretical and experimental plot for each, compare them percent difference, and then only write your lab report on the rolling disk. So relative to what y'all have been doing in HOL, pretty simple lab. So guess that'll do it. That's it for Physics 111. So if you're be in Physics 112, I'll virtually see you when you get there. But for some of y'all, this is it for physics. Y'all need 112. So I'll virtually maybe talk to you later through this. You have a good one.